Welcome. On behalf of the National Transit Institute, I thank you for participating in the Transit Capacity and Quality of Service Manual Rail Transit Capacity webinar. The National Transit Institute develops, promotes, and delivers training and education programs for the public transit industry in the United States. The webinar format consists of a presentation followed by a question and answer session. We are pleased to have Foster Nichols with us today. Foster Nichols is a Principal Professional Associate and Manager of Transit and Rail Operations Planning at Parsons Brinckerhoff. Foster holds a degree in Civil Engineering from Princeton University. He specialises in the planning and design of passenger rail systems and terminals. He has directed the development of long-range strategic plans for 4 major commuter rail systems: the Long Island Railroad in New York, the MARC system in Maryland, the Virginia Railway Express, and the Metro Rail system in Cape Town, South Africa. His transportation systems planning experience encompasses commuter rail new starts proposals in Ohio, Georgia, and North Carolina, and heavy and light rail transit systems in New York, New Jersey, Maryland, Washington DC, Chicago, and Los Angeles. He has helped design the Moynihan Station project in New York City, develop a master plan for Union Station in Washington DC, and prepare high-speed rail plans for California, New York State, and the Northeast Corridor between Washington and Boston. Now I will turn the presentation over to Foster.
Thank you very much, Michael. And good afternoon, everyone, or I guess good morning for those of you joining from the West Coast. As Michael mentioned, we'll go through a presentation and leave room at the end for questions and answers. For today's presentation, we'll run through quickly what our objectives are in this overview of the rail transit capacity section of the manual. We'll run through kind of a primer on the factors that determine and constitute rail capacity, both in terms of vehicles and probably most importantly, people. We'll explore the subject of design capacity or practical capacity and how that differs from the theoretical or absolute maximum capacity of a transit system. We'll run through really quickly the generalized estimation method for all kinds of rail transit systems, and then talk about a couple of special case applications where some different factors come into play. In terms of our objectives for this session, we are looking to understand those factors that influence rail transit capacity. What are the elements that comprise capacity? As I mentioned, to understand the distinctions between practical and theoretical capacity, and understand why, for purposes of systems planning, the most important thing is design capacity, not theoretical capacity. We're going to get familiar with the generalized method for capacity analysis and understand some special case conditions. This most recent effort to update the manual really continues the good work that was done previously to build this TCRP document. Some of the things that are different in the 3rd edition, there is a discussion on the differences and distinctions and respective roles of detailed simulation modeling versus sketch planning, which is really just a fancy word for using spreadsheets in evaluating rail capacity, and where you need the detail and where you can get by quite well with the spreadsheets. There is an improved discussion on the role of the vehicle platform interface, in particular how vehicle design and station design revolve or influence dwell time in its role in capacity. There's a new section on street running transit operations, streetcars and light rail in-street operations and preferential treatments and how that affects capacity. There has been a more standardized way to consistently present the equations and the capacity formulas in the manual. The actual calculations and the results are the same as before. Rail transit capacity really are a function of the laws of physics mostly, which haven't changed since the second edition. But there are some better ways and a little bit less cumbersome ways to present the formulas. And the same thing is true in the spreadsheets that accompany the physical manual. Those spreadsheet tools and models have been updated. Okay, now overview of rail and transit capacity. What are the factors that play into that? There are really two things you measure in a capacity analysis, and I think most of the folks that are signed in today are in the transportation systems planning field or interested in that field. The uses to which capacity analysis is put include figuring out, what's the capacity of the system I'm studying, what kind of investments might I need to make to increase that capacity. Perhaps for a new system, generally, what's the balance between my projected ridership and the kind of system that I'm building, and maybe even in early planning, what's the most appropriate mode and type of system that I should be thinking of for the market and the place that I'm studying. So we look at both line capacity, which is the vehicle or train side of the equation. How many trains or transit vehicles can pass a given location during a given time period. We usually measure that at an hourly basis, or sometimes we look at the minimum practical headway or separation time between vehicles. And then we also look at person capacity. How many people an hour can we handle down a transit or rail line or as part of a system. And that capacity definition, again, is for operations that are normal. So it's, again, not the maximum possible number of people, but the number of people that can be carried reliably and safely and with predictability on a system. Unless it's noted otherwise, the manual defines capacity as design capacity, or otherwise referred to as practical or achievable capacity, which is different from the absolute maximum or the theoretical capacity of a system. So you can only get to kind of the upper end of throughput capacity when the service is totally reliable, passenger behavior is completely predictable, every seat or occupancy space on the vehicle is filled up, and everything runs perfectly, which of course never happens in the real world. So as planners and analysts, we're really looking at trying to represent real world conditions and scheduling for and developing plans for the right size facility that's based on real world conditions. And so design capacity and practical capacity are intended to represent those real life days when things can go wrong. Passenger and vehicle and train operator performance are variable, and service has a certain amount of variability built into it, which is how every transit system in the world actually operates. The factors that play into calculating capacity include dwell time at stations, the characteristics of the signal and train control system, a concept known as operating margin that we'll get into, defining the minimum headway or time separation between successive trains on a line, looking at junction points or multiple line intersections, looking at turnbacks either at the end of a line or in some cases midstream, and also looking at the power supply capacity, a factor that sometimes is easy to ignore when doing planning. First with dwell time. Basically, dwell time is defined as the length of time that a train stops to serve passengers at a station. And in systems that operate at close headways, so most rail transit systems, subway or metro type systems, it is the station dwell time as much as anything that governs the fundamental capacity of the system. The factors that contribute to dwell time include the volumes of passengers getting on and off the train, probably the most important factor. But also the distribution of those passengers along the platform, particularly for systems where trains are multiple cars long. And the dwell time is governed by the heaviest load at the heaviest door. Generally, in all aspects of capacity planning, it's the weakest link in the chain, or the piece that has the least practical capacity that governs in the overall calculation. The number and width of train doors and basically how the vestibules on the train work affects the load, the rate at which people can board and alight from a train. Similarly, the vehicle height. Dealing with wheelchairs and passengers with mobility challenges are a factor that affects dwell time, and how the station is designed and how well that syncs up with the design of the vehicle can have a significant effect on that aspect of dwell time. Crowding levels, passenger behavior, whether or not your customers are well trained and step aside and allow people to enter and leave the vehicle unimpeded, or whether folks stand at the door and block flows can affect travel. Likewise, fare collection method, particularly for light rail or streetcar type systems, onboard fare collection and the queues of boarding passengers can be the controlling factor there. In addition to the time spent with the doors open, additional time between when the vehicle stops and when the doors open, and then also after the doors close and before the vehicle starts, also play into dwell time. And where that's done more efficiently, dwell times can be shorter. Basically, this graph shows the relationship between lengthening dwell time and the total capacity of a transit system for a typical close headway operating system. Again, for a rail transit line mostly. And if the dwell time is in the range of 30 seconds, basically the station doesn't control the capacity. It's the signal system and the vehicle dynamics that do. But as your dwell times lengthen to a minute or more, the dwell time really becomes the controlling factor, or to put it another way, the signal system might allow a following train to close in, but that train can't enter the station until the preceding train has finished its business and departs. And so it's that station dwell that becomes the controlling function. And when you get up to a minute and a half dwell time, you have cut your practical capacity by about a third. The signaling system for systems where dwell times are in good shape is the thing that controls a lot of systems. Signal system will control or govern the minimum safe spacing between trains. Again, this is the part of it that is related to the physics of vehicle movement. And the more accurately a train's position is known, the closer together the trains can operate, resulting in higher train throughput. There are a bunch of different types of signal and train or vehicle control systems. All of them affect headways. For those of us in the planning business, tend to think of signal system design as a black art, kind of like ridership forecasting or econometrics. But the good news is for capacity analysis purposes, you really simply need to get to either the signal designer or the system spec and ask a couple of questions about how the system measures capacity. Types of signal systems. Fixed block is the traditional most common method for a rail transit system. which involves the definition of specific physical segments of the transit line with basically a signal controlling access to each block. And those of you that have seen kind of the control boards in transit control systems with the blocks identified and red lights that show the trains occupying a block, that's a fixed block system. Generally, a traditional signal system allows or requires the succeeding train to keep one clear empty block between trains occupying the block. And so a train is either occupying a block or it's not. So it's a relatively coarse function, and the spacing and the speed of the trains and the performance, acceleration and braking performance of the trains all affect what the throughput is on a fixed block system. Cab signaling was an enhancement that provides for a greater number of displays of allowable speed to the operator of the vehicle. Basically, instead of visible lights and control cables along the right-of-way, information on the permissible speed of the train is passed actually through circuits in the rails to the operator of the following vehicle, and they get a display in the cab of how fast they're allowed to go and whether they need to stop at the next block or proceed. So that greater variability or greater choice in the kinds of commands that are given to the vehicle operator allow a little bit closer spacing for the same kind of length of fixed block. The latest innovation in signal and train control systems is moving block, and there are different ways that moving block signal systems are defined, sometimes referred to as transmission-based or communications-based signaling. These are systems where the physical location of the train or the transit vehicle is not identified by occupying a circuit on the track, but either through a train positioning, GPS type technology or other comparable system. And the location and the speed of the train is known precisely to the overall control system, and therefore instructions to the following train on how closely it can close in behind the first train and how fast it can go can be given in real time. And those ongoing computer calculations basically govern the performance of the network in a way that is still safe but more optimized with respect to the headway and ability of trains to close in on each other in a network. So moving block potentially gives you the highest capacity. This set of curves shows again the relationship of these different signal train control technologies to capacity, also with respect to the line speed of the system. The important takeaway here is that higher speed is once you get up above 20 to 30 miles an hour, higher speed is the enemy of capacity. And the faster you want to go, the faster the top speed limit. Actually, the fewer trains per hour you can get across the network. And again, that is due to the physics of train movement and the fact that it takes longer to stop a train at higher speed than it does at lower speed. It's kind of the same phenomenon you experience out on the highway, where as traffic starts to congest, the speed slows down so that more traffic can operate over the network, at least until you get to the point where you start to hit delays and stop and go traffic, and that's kind of the low end of the curve where you start to lose capacity again. So moving block gives you the best performance, fixed block, cab signaling somewhat less. The basic parameters of those systems generally can come from the system design specifications, from looking at comparable technologies, and there are some rules of thumb that can be applied where you don't know the details of the system. Third factor affecting capacity is the concept of operating margin, or this is kind of the safety factor. So you You don't want to design a system where the following train has only enough space to stop before it hits the one before, or before it hits a red signal. You need to allow for real-world conditions, and this is really the major thing that gets added to a theoretical capacity estimate to allow for a more comfortable, practical level of throughput. Variable station dwell times having to do with passenger loads or stuck doors on the train or other factors is accounted for in this extra allowance. If you don't have enough of an operating margin, if something happens at the station and the dwell time is longer than scheduled, you can start to delay the following trains. And if your overall margin is too low and you've got too many trains scheduled in a short amount of time, those delays can propagate or cascade through the network. So there are examples. I've done a lot of work in New York with the railroads, and because of the volume of traffic, that operation is scheduled with relatively small operating margins, simply to physically carry the number of people that need to get in and out of Manhattan every day. A consequence of that is when there's a problem, when there's a delay, it doesn't take much of an incident for those delays to cascade through most of the rest of the rush hour, which is not something you want to design into a system if you can avoid it. So planning for an appropriate operating margin is a good thing to do. The manual recommends some rules of thumb for existing operations where what the typical dwell time is, planning for 2 standard deviations of that dwell time, or really at the point where between 2 and 3% of all dwells can cause a delay to the following train is an appropriate design standard. Generally, for, again, a rail transit kind of operation at close headways, an additional 15 to 25 seconds added on to all of the other things that estimate your minimum headway is a good margin. And what that allows is, again, when things happen, the cascading delays back through the system can be absorbed within 1 or 2 subsequent train movements, and then the system recovers. Another general observation is actually it's where you can measure things on an existing system and use good empirical data to do your planning. That is always preferred over the cookbook kind of standard estimates that appear in this manual or elsewhere. And so this is all good guidance, but where you can actually replace assumptions in these capacity calculations with good empirical data from your system or a good comparable system, that is almost always preferable. The graph here relating capacity to operating margin kind of shows a similar relationship to the one we looked at before with dwell times, and it simply shows that the more operating margin you have, the lower your capacity is. It's kind of counterintuitive, though. It looks from this graph like operating margin is a bad thing because it cuts capacity, but in fact, operating at 100% of capacity on this graph means you've got less margin for error, if you will. And so actually, I'd say the vertical axis in this chart is kind of representing theoretical capacity or capacity without margin. And you want to be down closer to that 75 or 80% level to have a stable system. So the 3 factors that we've just run through added together gets us to the minimum non-interference headway, which is kind of an awkward term, but really represents the practical minimum headway of a system. And if you take that number, divide it into an hour or 3,600 seconds, and then round down, that gives you the practical line capacity in trains per hour of your system. So for a piece of system that is a straight line system where all the trains basically perform the same, every train stops at every stop, and it's kind of a predictable piece of single running line, that's the capacity calculation. Other things that factor in, curves and grades change train performance, and so there may be places where you lose the ability to maintain a close headway operation, and that would be an additional margin on the headway. And the other thing we'll look at coming up here are some of the other things in a rail or transit system network that affect capacity. And in all cases, these are things that will generally constrain capacity or add to the minimum headway in addition to the basic line calculation that we've just talked about. All right, here's a graph that kind of puts all the pieces together, and it is worth here spending a couple of minutes talking about, although I know we have to keep moving here. It is a time distance diagram, really the basic tool for transit operations planners, I think, and it's known in some circles as a string line diagram. I guess dating from the days before computers, suppose even the days before pencils and graph paper, when you'd tack a piece of string with thumbtacks up on the wall to show the movement of a train in space and time down a line and through a network. Here's a picture of a train pulling into a station. It stops, so it's not moving as time goes by for the dwell, and then it moves on. And the key way to think about capacity is, all right, how soon can the subsequent train follow? And so this time difference here is actually the minimum practical headway. And you can see here the influence of dwell time and safe stopping distance. So if you didn't have stations to deal with, basically the separation between the dash line and the solid line, is all you'd need. So physically moving the trains, that's what the signal system would allow. The introduction of the dwell time plus that train separation time plus your operating margin, which is this little bit here in the middle, is really what defines this good steady state headway. And so your peak hour through this station would have a series of trains following the shape of this string line graph. Junctions on the system are or can be a constraint. There are two kinds: flat junctions and flying junctions. Flat junctions are at grade, like the picture here, and many railroads, most railroads, have flat junctions at points where lines interconnect. Light rail transit systems generally do. Most heavy rail or transit systems are now designed where line junctions are grade separated, which permits higher throughput and reduces the potential for conflicting train movements. Basically, at a flat junction, like at a traffic intersection, you can only move one train at a time, and so trains looking to take other paths or move in other directions through the junction can't operate when that happens. If you add up all those movements over the course of an hour, each segment up and downstream from a flat junction has less capacity than if the junction weren't there. Generally, in a transit application, you can get through a flat junction at headways on the order of 2 minutes. Some of the older legacy transit systems, like the Green Line in Boston and pieces of the New York subway system, actually have flat junctions, and they do crank trains through at close to that 2-minute headway level. But there is potential for train interference, and generally in modern transit system design, we try to avoid that for close headway operations. So if you get to 2.5 or 3-minute headways and are looking to run a robust service, generally these grade separated or flying junctions are preferable. Even with flying junctions, as a network gets complicated and you have multiple flying junctions, again, the potential to encounter a delay or a train from another branch in your way increases. And so the more of these junctions and the more complex the network, the less the overall practical capacity of any single piece. So that needs to be taken into account as you plan a network. Turnback locations, these are found at every end of the line location, and depending on how that is designed, what your line headway is, and how you operate the turnback, it can have an effect on overall line capacity. Generally, in system design, you don't want your terminal to control line capacity, and so good design of these facilities when you're in the planning stage can help make sure that you can get the service up to the headway you need to carry your passengers. Although if you're analyzing an existing system, understanding how the terminals work is important, because there are many examples where, particularly with older legacy systems, the actual capacity constraint on a line may be the terminal and not the running line segment. The picture here is of a typical terminal station with two stub tracks and a universal set of crossovers ahead of the station. And at the peak, you feed alternate side to the station. The train turns and operates back in a way that keeps the headway going. The turnback time, which is something that needs to be calculated, is a function of passenger service time, how long it takes you to alight and board the passengers. If the same operator is going to operate the train in both directions, he or she has to walk the full length of the train and perform whatever safety check is required to operate in the reverse direction. And you've got to be able to clear the crossovers or the interlocking that's in front of the terminal. And then, as everywhere else, an operating margin needs to be applied. And so all of that time factors into when the track that's occupied for a turning train frees up. You can see here an application where sometimes adding a third track to a terminal could be one of the fixes for making sure that the end of the line facility isn't your constraint. Other things you can do is actually have a second operator or driver who's positioned at the opposite end of the platform. You've got to hire one more staff person, but that allows you to cut out that walking time for the operator, which for a long train, if you're looking at a 8 or 10 car transit train, can be several minutes. In addition, you can design a terminal with crossovers beyond the terminal station, so the station becomes a traditional drop and go, and your layover occurs in a far side yard. That consumes more real estate and adds some cost. You can also increase the number of platforms, or employ a loop, which again is kind of a traditional trolley car solution, can consume more real estate, particularly if you're street running. But does cut out some of that time at a terminal platform. And then finally, the traction power or propulsion power constraints. And this is something that's easy to forget when planning a system. Actually, planning a new system, it's generally designed in. When you're looking to take an existing system and significantly increase the volume of train movements and the passenger carrying capacity, you can bump into the limit of what the existing traction power system can deliver. And so a separate analysis is sometimes required. And in this case, going to the folks who know the capacity of the traction power system and can work on that is important to factor in. So something to keep in mind. In the commuter rail world, other vehicle-related constraints are simply how many cars can be pulled by a locomotive. And as locomotive technology improves, actually the carrying capacity has increased in recent years. A good planning parameter for typical new system might be an 8-car train. But there are examples out there on the heavier lines where the new locomotives are being designed to be able to pull 10 or even 12 85-foot cars. So rules of thumb for capacity planning. Again, absent empirical data or good comparables for a light rail system on a largely dedicated guideway, 20 trains per hour is a good rule of thumb. For street running, I'll point you to the examples in the manual itself for other factors to be taken into account that probably reduce that number. Fixed block transit systems up to a 2-minute headway or 30 trains per hour with cab signals and cab controls, slight increment on that. With moving block technology, again, a slight increment over that as well. Again, these are design capacity figures, but just broad rules of thumb. And again, these are systems where the stations and extra long dwells are not the constraint. So they're not a substitute for doing the full analysis. And again, better to use actual empirical data than these planning factors. But for a first cut analysis, for analyzing something new, these are good rules of thumb. So here's the overall equation on capacity from the people side of things. We've talked about trains and vehicles so far. So people capacity is a function of the train capacity, numbers of trains per hour. How long is the train? How many cars or vehicles in the train? What is the passenger capacity? For something like commuter rail, you'll measure seats. For a transit vehicle, it's seats plus normal standing load at a reasonable occupancy factor, and then a peak hour factor. And we'll get back to what that means in a minute. Train length in a system is constrained by the size of your fleet. So you need to have enough cars available to fill out the train lengths. But there are also some physical factors at play. The length of station platforms. For a street running system, the length of your city blocks actually governs the capacity, and how the train cars are configured themselves, and what the conditions are in terms of how many square feet per person are acceptable for a loading for standees, all factor in. And there are good rules of thumb in the manual and available elsewhere for kind of typical car capacities. The peak hour factor is something that basically allows the analyst to take account of the micro peaking that occurs within a peak hour. It is rare for a transit system to have even loading across a whole rush hour. Some of the very heavy systems approximate that, but typically there is a bell curve or a jagged curve, like in this graph, that shows peaking within the peak hour. But it's often convenient to do capacity planning on an hourly basis, and so this capacity calculation needs to apply a factor to the hourly number to get at what actually you can carry in an hour, assuming this bell curve shape on demand. And so, again, good rules of thumb might be to take your hourly design capacity and multiply it by 80% to get the actual practical people moving capacity over an hour. Light rail and commuter rail might want to apply a slightly larger discount factor. Loading diversity reflects the fact that in a long train, not every car is going to be evenly loaded. Some cars are going to be located closer to the stairs and exits from key stations, and how the station is designed and passenger behavior patterns, will affect how the trains load up. In commuter rail systems, even things like where people's parking is out at the end of the line, or which car do you meet your buddies in for the daily card game on the way to work, affect where you sit and stand on the train. The point there is, in a train, even at rush hour, not all capacity is going to be evenly used. And you even find in some systems that there may be standees in some cars and available seats in other cars. And so understanding that loading diversity and planning for the right average condition are more important than simply basing your calculations on uniform behavior characteristics. So fundamentally, theoretical capacity, this is if you talk to the vehicle manufacturer, if you talk to the signal system designer, this is the number you're likely to get from them. How many trains an hour, how many people an hour will physically fit on this system, and that's your starting point. But it assumes kind of a perfect world, perfect loading, perfect passenger behavior, which is never the case. And so what we want to develop for planning purposes is an estimate of design capacity or practical capacity. It is always less than theoretical capacity due to all the factors that we just talked about. And again, importantly, it tends to have an inverse relationship with line speed. So the faster you want to go, the less your practical capacity is as a percentage of theoretical capacity. And that can get pretty interesting when you start looking at things like high-speed rail systems or systems that want to have several different kinds of trains or vehicles operating at different speeds. It tends to really start to eat into available capacity. So that's the overview of concepts. We'll run through now kind of the general calculation method for applying the factors, and then we'll talk about some special cases. This generalized method is a good approach for most types of rail transit. It's good for an initial exercise if you're looking to do a quick calculation on capacity. There are some special cases, particularly in the realm of commuter rail for automated guideway transit or people movers, and things like gondola systems and funiculars and others that are classified in the manual as ropeways. And we'll talk a little bit about those at the end. So, step one, determine that non-interference headway, the combination of the station dwell, what the signal and train control system can deliver, and the operating margin calculation. And those three together give you what your line headway is. Step two is to look at, are there any special things that are happening in the configuration of your network other than a straight two-line transit operation with no interference. One thing that we hadn't talked about is a single track operation, and there are lots of examples of these, particularly in commuter rail applications, but also in light rail and transit applications, where in order to save money or because of physical constraints, there may be portions of a network that have single track operation, where trains occupy the piece of single track in alternate directions. And there, basically, you've got to take your line headway calculation and multiply it by 2 to allow for a train moving in each direction over the piece of single track. For on-street operations, the on-street operations that go through signalized intersections, the capacity of the traffic signals also plays in. And so, again, twice the signal system length or the dwell time-based calculation, whichever is worse, whichever is the weakest link, governs in the calculation of capacity. For transit systems or rail systems that have grade crossings, and where there's a grade crossing at a station, it is typical to have the case where the crossing gates remain up while the train is dwelling at the station, but then there's a manual activation of the gates, and so that additional time has to be factored into the line headway. In all cases, the minimum headway is the worst case condition or the weakest link in the chain, and so you take your design line headway and reduce it from there based on special conditions. Next thing to look at are your junctions. Look at the network configuration. How many branch lines, how do they connect? Are they flat junctions or grade separated flying junctions? And at these locations, you may need to look at the actual amount of time that it takes trains to pass through a junction. And so the train control system, train length and speed influence that. The actual design of the junction in terms of the switch angle or the turnout number influences actually how fast a train can move through a switch. And whereas your main move through a switch might be at the line speed. Your merging or diverging move might be at a slower speed, and so the train making that move occupies more time, and therefore that move will govern the headway. And in all cases at junctions, there is an additional operating margin that needs to be applied to account for the variability of trains arriving at a junction point. Even though the train schedule may have them a comfortable 2 or 2.5 minutes apart, if you've got a minute delay on one line, that can result in delay and congestion, and that kind of performance tends to cut into the overall throughput capacity of the line. And then the fourth and final step, check the power supply limitations if you're looking at a change that substantially increases the volume of train movement activity on an electrified system. And these are all pretty much special case locations that are conditions that need to be looked at individually. The controlling system headway is, again, the worst case of those 4 calculations on headway, and so you always take the lowest common denominator for your measurement of line or system capacity. It's important to check what's going on at terminals. Are the terminal locations, in fact, the constraint on the capacity of a network or a stretch of network? We looked before at turning back at terminal points. Many systems also have turnbacks at intermediate locations where extra tracks, sometimes known as pocket tracks or side tracks, are provided. Those turnback moves can be done without affecting following train movements. But there are lots of examples of systems where trains are turned short on the line, and so you have to look at that basically as a dwell on the train as it turns, and so following movements from further out on the line will be constrained by that turning time. For a typical turnback at an end of the line station, again, the time to make the turnback move is what controls the terminal capacity, and so if that layover time is more than twice the line headway, the terminal is likely to be the constraint on the operation, and so either changing the terminal configuration, changing the operating behavior, introducing an extra driver or shortening dwell time is something to look at. If none of that is possible, then that's the case where actually the terminal is what governs the overall line capacity. And the final step is to convert it all into an hourly figure, which is dividing your headway into the number of seconds in an hour. And so back to our equation here. The person movement capacity is the train headway times the train capacity in terms of numbers of cars and car capacity, and the peaking factor, so that you can represent in an hourly number the actual distribution of demand over the course of an hour, which does vary in most systems. With respect to some special cases here, we'll talk about commuter rail for a moment, where there's some additional things to consider in network and capacity planning. Capacity estimates, it's not so much that the calculations are inexact, it's just that there are lots of other things going on in the typical commuter rail network that are beyond the calculations that we just talked about. In most cases, commuter rail systems are operated on tracks and systems that are owned by the freight railroad companies and on which freight trains operate. And so, yeah, it's true that the number of passenger trains that can be operated on a system is not so much a function of the capacity calculation, but it's actually determined by negotiation and contract with the host railroad. But capacity analysis plays into those negotiations, and so being able to understand how commuter trains and freight trains interact on a network is really part of figuring out what the terms of those agreements should be. And because freight trains and passenger trains have very different levels of performance, as we'll see, what goes into the capacity calculations tends to reduce significantly the total throughput capacity. It's also true that in the commuter rail world, there's a wider variability in the performance of the types of equipment that are out there. And so understanding how locomotives and train sets operate is more important generally than in the rail transit applications. And you get some weirdness and greater variability in the way the networks are configured in terms of what terminals look like, what junctions look like, the mixing of single track and multiple track segments. There are different ways in which the networks are defined, which makes calculating capacity a little bit more complicated. Where you've got mixed traffic, actually understanding how all of the different kinds of trains perform on the network may require simulation modeling, particularly for higher density operations, to understand what can work. For systems where you're not looking for running at the practical minimum headway, sketch planning or hand calculations still can suffice in those circumstances. The manual doesn't provide a lot of detail on commuter rail capacity calculations, but is a pretty good compendium of the things that need to be considered on a commuter rail network, particularly in mixed traffic or blended traffic operations. One of the things that can occupy and consume track capacity, the speed of trains affects capacity on a network, and again, higher speed is the enemy of capacity in general. Where trains come together on the network, often at flat junctions, those are locations that generate delay. The variability of meeting schedules at those junctions increases the risk of there being delays and the chances that you run into conflicts and problems on the line. Those potential conflicts are more prevalent where you've got different kinds of trains operating on the system, and that can be passenger trains with freight trains, commuter trains with intercity trains, or even high-speed trains where their speed and physical characteristics are different. It's also true on railroads, and frankly also on transit systems, that there are other activities out on the line, inspection and maintenance activities that are ongoing. Often those can be confined to the non-passenger carrying hours overnight, but if it's a freight railroad owning the track, they may be out there doing work during daylight hours when it might be affecting the passenger operation. The condition of the rail and the track and the right-of-way itself can affect capacity, and there are places on the commuter rail network where track conditions result in temporary speed restrictions and basically a separate capacity analysis and often a separate train schedule is required to deal with those conditions as they arise. Passenger station stops, stations that can have a wide variety of physical configurations and therefore pretty variable dwell times can affect capacity. Freight industrial switching and the need to access side tracks for handling freight customers come into play, as well as working around bigger yard installations and dealing with train control system failures in general. Planning for when things go wrong is an important part of capacity planning for any system. You do that for a transit system as well, but there's probably a slightly longer list of things to be considered in the railroad world. Same goes for incidents and weather conditions like fall leaves on the tracks or hot weather potential for effects on either the track or in electrified systems that run off of catenary systems, effects even on the traction power system. Other factors for commuter rail include the performance of different kinds of trains, and the fact that freight trains are longer and heavier, take longer to stop. Basically, the signal system design on freight railroads is geared to freight trains, which results in longer blocks and therefore generally less capacity for passenger trains. Even if the freight trains aren't there, the passenger trains have to meet the requirements of that signal system. Also, commuter rail can be in some systems focused mostly on the rush hour direction, and so understanding actually how the service works in both directions of travel can affect capacity calculations. And likewise, the physical configuration of tracks and terminal stations is more complex. Operating practices can be different. In commuter rail, in many cases of higher volume systems, not every train is an all-stop local. And so there are zone expresses where trains may stop during a portion of the line and then run express over the rest of the territory. Skip-stop service, which you can see in commuter rail and transit applications in some places, affects calculations. Likewise, in a commuter rail system, something not to forget, you can make the system work in terms of the track, in terms of the stations, but you also need sufficient storage capacity, both out at the end of the line and in many systems close to the downtown terminal for midday storage. And all the systems work as an overall balanced network, and the capacity of the overall system is governed again by the worst case. And so there are examples of commuter rail systems out there where the constraint actually is the size of the storage yard, and not so much either the size of the fleet or the capacity of the line itself. And for commuter rail systems where you're not generally running at 2 or 3 minute headways in most applications, the station dwell isn't as important as the line capacity and the yard capacity considerations. Ways to improve the capacity of a rail network, if you've got a lot of single track out there, if you've got flat junctions, going to double tracking and selective grade separations can be effective ways to increase capacity. You got to look at the cost of all those improvements, though, against the benefit in terms of train moving and people moving capacity. Often, if you're able to simply lengthen the train, take advantage of those new powerful locomotives, that often is the least expensive, sometimes the most cost-effective way to increase the capacity of a commuter rail system. When you lengthen sidings or lengthen double-track sections, generally making them long enough to be able to do a running meet or running overtake as opposed to one where the train has to stop and wait for the train in the other direction is better in terms of performance and can be for capacity. And so fewer longer passing sidings can be better than lots of short sidings that force a lot of stopping and going. Improving the speed of diverging and merging moves with better switch turnout geometry, looking at the train control system, and looking at the overall balanced configuration of the network are all things to be considered in looking at commuter rail capacity. Moving on to people movers or automated guideway transit. These are, by and large, more proprietary purpose-built systems, and so for a new system, one can rely on information from the manufacturer, from the system design to understand capacity. I'd say with the caution that generally what you're going to see in literature is going to be a measure of theoretical capacity, and you'll want to look at the operating margins and other factors that bring you down to a more realistic practical capacity or design capacity level. It's also important to note that specialty AGT systems can be quite different from transit applications in terms of passenger behavior and therefore capacity. Most of them, aimed at specific markets that either require longer passenger dwells or dealing with specialty loads of passengers. And so the standard capacity calculations may be less applicable in those kind of purpose-built facilities. One possible way to increase the capacity of an AGT system is to look at offline stations. That adds to the complexity and cost of the network and the associated train control system. But there are some applications of that for higher density type AGT systems. And then finally, ropeways, which are really of two types: reversible systems, such as aerial trams or funiculars, where vehicles shuttle back and forth between terminal stations on a dedicated track or line, and they're basically the dwell time plus the length of time it takes to traverse the line is what dictates the capacity of the system, a relatively straightforward calculation. Then you've got continuously circulating systems, where basically the line speed, the spacing between vehicles or carriers influences the capacity. One thing to say about those kinds of systems is once they're built and installed, it can be pretty hard to go in and if they're not sized right for the load, hard to go in and significantly increase the capacity. A word here before we wrap up on the difference between and the applications for doing sketch planning versus detailed simulation. Sketch planning or spreadsheet-based analysis is a great tool up front, basically taking the calculations that we've just gone through and baking them into a spreadsheet format can give you good ballpark results up front. That's a method that can be quickly deployed to initially scale and size an operation, and you can come back later with more detailed tools to get to the specifics. It's also the way you look at studies or projects where you've got multiple alternatives and you need to winnow that field of options down to a smaller number. So looking at multiple modes, looking at multiple network and station configurations, different operating or system plans, a comparative analysis in the sketch plan mode can give you the ability to pick the best options, and then you can go back and understand them better once you've narrowed the field. It's also the way to look at relatively simple systems that don't have a lot of network complexity, don't have a lot of variability in them, and where you don't really need to look at the dynamics of train and vehicle operations. And where you're simply limited in terms of time and money, the sketch planning tools are a good way to get the best value for your resource and in terms of understanding capacity and capacity requirements. Simulation models, on the other hand, are becoming increasingly sophisticated and relied upon to determine exactly how well systems can perform and to optimize the level of investment for what you need to be able to deliver on a transit system or a railroad. They are in the commuter rail world with freight railroad owners or with Amtrak really now part of the process of new investment planning, and before the business deal gets done for a new system or a major expansion of an existing system, the proof of the required infrastructure solutions and the proof of the ability to handle the changes in passenger traffic generally get run through a detailed simulator. There are several off-the-shelf packages that are in common use, and all of them take some training to be able to utilize, but they're becoming certainly part of the framework of doing major studies. Sometimes the big models are really what you need to understand real big or complex terminals. A place like Penn Station, New York, Washington Union Station, even some of the big complex transit terminal station operations where you're looking to crank down headways as much as possible. being able to model the terminal and turnback configurations is important. Also, where you're looking at multiple kinds of stopping patterns, overlaying local and express services on the same track, and how the trains close in to each other, how you might overtake local trains with express trains, with special portions of passing sidings. That can be pretty complicated on a high-density network. And investment grade analysis again refers to what you need to do to get that business deal done, either with a host railroad or to justify to those who are providing the funding for your improvement that they're getting value for money, best value for money in terms of the investment. It does take time and resources, however. So the combination of sketch planning and simulation, often on the same project, can be an effective way to do early planning, cut to the chase in terms of what the important options are, but then in the end, have that confidence that you actually have justified what you want to do. That basically wraps up the presentation. The materials, this slideshow, as well as the manual itself, and some of the key reference documents like TCRP Report 13 are available online. And so I'd encourage you to take advantage of those documents. The manual makes a good addition to your bookshelf and some good bedtime reading, particularly if you have trouble falling asleep. There's a lot of good equations and detailed stuff in there. And please feel free to avail yourself of it. I'd like to acknowledge the good work of many people in producing the update to the manual and in putting this show together. In particular, Paul at Kittleson, Alan Danaher at PB, who's led our effort. Arab, who were involved also in reviewing the rail transit capacity chapter. And I'd also like to give a shout out to Mike and the NTI crew, who really made setting up and giving this presentation very easy and seamless. And so it takes a lot of hard work behind the scenes to get that set up, but we certainly appreciate that. At this point, I think that it concludes the presentation. I thank you very much for your patience on kind of a dry and arcane subject, but hopefully you have a sense of what's in the manual. Thanks very much.